Guys. Believe it or not, that's the only time it's the second time in my entire teaching career I've started a class late. First time was several years back, so, no one's perfect, but yeah, I just want to make sure the new GoPro, not a new GoPro, but just want to make sure the GoPro is configured with the new capture card and all that good stuff. How's everyone doing? It's good to hear. So today we'll be talking about Chapter 4, which of course is the current Ethernet specifications. And just to remind everyone in here, this class is, kind of starting a little bit basic. Some of the stuff today will be a review from last class when we talked about Chapter 3. So we're going to go kind of briefly over a lot of it. Some of it we'll skip completely because it's just a complete review. But that's pretty much what we're doing today, really covering Chapter 4. So having said that, we got a couple minutes. Who wants to share a cool experience with the networking team? What you think? Okay, very cool. Anyone else want to share experience from last class? Or whenever you did the tour? Like I say, I'm passing around a thank you card. If you just want to sign it, that's fine. If you don't want to sign it, that's fine too. If you want to write a little message, like really appreciated it, whatever you want to do, that's fine. So having said that, we're going to go ahead and jump into the material. So it's going to be covering networking basics, which we've talked about quite a bit in here. So we're going to get a little bit more in depth with the basics. Pretty much it. Ethernet basics, that's really what we'll pick up today. Ethernet in the data link, as well as Ethernet in the physical layer. We're going to skip most of Ethernet in the physical layer because it's literally just talking about cables. You guys had cables in Chapter 3, so just don't forget everything you learned previously and you'll be all right. And then lastly, we'll talk about Ethernet standards just a little bit. So, that out of the way, of course, we know that in a network, there's really two major addresses that we use to sort of communicate. The first is going to be an IP address. Now, with IPv4, in most cases, is an IP address going to be unique to a device? It's not. There's a limited number of IP addresses, and because of that, we can't have every IPv4 address be unique to a device. So with IPv4, what are some ways we get around that? We'll talk about network address tunneling in future chapters, but for now, just understand that the IP address, we're going to think of that as an external address. So think on a letter. You guys ever sent a letter before to someone? So what would the address be? Like the physical address, like for example, 123 Sesame Street. What's that? Is that a MAC address or is that an IP address? So that's going to be like an IP address. And then the MAC address is going to be like the individual. If you just put Elmo, well, Elmo's kind of famous. Give me someone who's not famous. How about me? Am I the only Andrew Miller in the world? So if you send a letter to Andrew Miller, is it going to end up at my place? Very likely not. So the MAC address is how it happens on the internal side of the network. It doesn't leave the router. And that's an important point to remember when we're talking about network communication is the IP address, think of that as like a traditional address, where you have where someone lives. Let's say you have, 4 people in your house, okay? And you don't put who the mail is to. Who opens it? Who opens the mail? Pretty much. So MAC address kind of prevents every device from opening it, assuming that we're not using a hub. If we're using switches and routers, it's going to prevent the packet from going everywhere. So that's what we're talking about. And then lastly, the process in which this happens is host name to IP address resolution. So this can be DNS, although not every device is going to have a DNS address on it. So of course, we're talking domain name service. Why would that be? Why would a regular desktop maybe not have a DNS address associated with it? What is a DNS address? It's basically like a URL. So, basically, host name is going to be used on a local network, and it's going to be tied to the MAC address of the device it's on. And of course, we know MAC addresses should be unique to pretty much every device. Now, having said that, are MAC addresses in practice unique to every device? So they're not, because while on paper they should be, a lot of manufacturers, less reputable ones, certain countries, you could probably take a guess at what I may be alluding to here, they don't necessarily have the best practices for making sure that a MAC address is going to be unique to the individual network interface card. So because of that, what happens if two devices on the same network have the same MAC address? What happens? Does it work well? No, it doesn't work well at all. So there can be cases, and also, two different types of MAC addresses. We'll talk about this in a couple slides, but they're not necessarily going to be a permanent address that does not change. So here's sort of an example of this process. We're just going to look at this briefly. It's covered in a lot more detail in chapters 5 and 6. But basically, you can see we have the source. So I think this is like Bob's computer or something. I don't remember. And in the destination, it's going out to the router, and it's asking it, what is the name of Sally? And so it's using the ARP protocol, of course, and this is what it literally looks like. Like if you were to pull up some sort of packet tracing software like Wireshark or something like that, you'd see something very similar to this. It's going to ask who has it, and it's going to say tell this person. And then the response is going to say who has it. So it's basically what you're doing there. So any questions up to this point? All right. Shift gears a little bit, get into some newer content. That's pretty much a review from chapters 1 and 2. Talk about collision versus broadcast domains. So a collision domain, does that sound, just looking at the name of what it is, does collision domain sound like something we should strive for to have lots of on a network? Why do you say not, Ben? So interference could be, but there's definitely going to be a lot of network congestion. So with a collision domain, basically what happens is, if you have a network and you send out communication, it has no way of knowing sort of what information is being sent to where. I mean, it does know that, but it doesn't necessarily know, like if I send information and you send information at the exact same time, it doesn't really have a great way to handle that. So let's say hypothetically we have a network that is using a collision domain, and let's say that it has different packets that are being sent out. And let's just say, for an example, that as each packet gets sent out, let's say Ben and I send out communication at the same time. So collision domain cannot handle that. It's going to have a collision event. Okay. So a collision event I have up here. Think of a car crash. Okay. What's a car crash? So if we have one car going this way, another car going this way, what happens when they crash? Well, there's going to be some destruction, unfortunately. Well, the good news is you're not going to destroy a network with a collision domain, but you will certainly adversely impact the speed. You will adversely impact the reliability. And, you can really only have this, well, let me rephrase that. You're most likely to run into this using hubs. It's not impossible to configure a switch or a router to use a collision domain, but why would you? I mean, you're just asking for trouble. Anyone in here asking for trouble? That's a good thing. So yeah, with a hub, of course, we don't have a way to route a packet to its actual destination. That's a huge problem because if we're much more than, say, 3 or 4 devices, is that going to get pretty congested pretty quickly? It is. That's why most things use switches. Switches, of course, don't have that problem because they can route by MAC address. And of course, we also have broadcast domains, which are basically going to be where we have it segmented. So if you have a packet, it's going to go to the destination. That's really all you need to know there. Does that make sense? All right, let's talk a little bit about the CSMA CD. So carrier sense multiple access with collision detection. So this is a very beneficial technology because it's going to prevent a lot of the issues you may face with these collisions. So it looks like the picture's cut off just a little bit, but you kind of get the idea. Where what's happening is without this collision detection, what's going to happen if we have a collision is it's just going to keep trying the same thing over and over. It has no way to say, you can send your packet first, then you can send your packet second. So you see here, A and C or A and D, I think, are both sending packets at the same time. And what happens is when they reach C, like the physical layer, there's a collision. And basically what this is doing, this is timing stuff. So it's saying you can send your packets, and then it's going to another device saying you can send your packets. So what it does, it checks for an existing signal in the network. If there is no existing signal, then it can transmit. And once we have a transmission with CIS, AMA, CD, we can actually jam other people from being able to transmit. So it's going to prevent these sort of collisions from happening. Now, what's the problem with this technology? That can be pretty congestive. Imagine if you had a network that was using just this technology. What's going to happen if you got 1,000 users all wanting to transmit stuff? Is that going to be a good way to do it? A little bit outdated, but it prevents congestion, but doesn't eliminate it by any stretch, because imagine A is wanting to download a very large file, going to basically eat up the whole network. It's not that useful, but prevents collisions, so they're not downloading huge files, or most of the time you'll be able to segment it and say, you can transmit this amount, you can transmit this amount through something like quality of service, which again is a later chapter. But now just kind of understand what this does. Just does it by timing. That's all we're doing here. Okay, talk a little bit about broadband versus baseband. So broadband is going to be where we have a cable that allows us to transmit multiple types of media. So the example in the book is like a phone line, which is going to be able to transmit an analog phone signal, as well as a digital phone signal, more common today than plain old telephone service, of course, as well as DSL at the same time. So it's going to be beneficial for a lot of different things. Let's think about some other examples of broadband, though. What about cable? Can we get cable television and cable internet service on the same cable? Yeah, we can. So that's another example of broadband. Contrast with baseband. Baseband is where you have a single cable for a single purpose. So for example, just a standard Ethernet cable. What can you transmit across an Ethernet cable? Now, excluding stuff like power over Ethernet, which is technically the same signal, I guess, but anyway. So basically, you can do one thing over it. And that has its advantages and disadvantages, but the gist of it is that cable has a single purpose with baseband. So it's not allowing us to do a broad number of things. Think about fiber. Which is fiber? It's a trick question because it depends on the type of fiber. You guys heard of dark fiber? The dark fiber is an example of broadband because you can have multiple signals going across the same cable. Whereas if you think like a traditional fiber patch cable, you can really only do one thing with it at a time. And in fact, fiber is kind of unique. Well, not necessarily completely unique, but you have one cable for transmit, one cable for receive with fiber. Technically speaking, with a standard Ethernet cable, you have the same thing where you have different strands of the cable, but still one cable technically. Does that make sense? Having said that, of course you can transmit and receive with a fiber cable, just a single cable, but what's the problem? You can't do it at the same time. So let's talk a little about bit rate versus baud rate. So bit rate, as the name would imply, it's going to be how many bits of data go across something at a given time. The SI prefix is going to be bits per second. What's the problem with that? Do we measure anything in bits per second nowadays? Why not? How big is a bit? It's not very big, is it? I'd be willing to bet that, you probably don't have many files that are expressed in bits or even, maybe megabytes, maybe even kilobytes, but a bit is tiny, So talking about bits per second, what's something we're more likely to see in the field? How about megabits per second, gigabits per second? Those are measures you're a lot more likely to run into. Of course, just know how many bits are in a byte. 8, exactly. So when you're talking about stuff like internet speed, you're talking about 50 megabits a second. How many megabytes a second is that? Yeah, somewhere in there. So, just kind of keep that in mind that the SI prefix, some derivative, actually the SI prefix is quite literally bits per second, but it's almost always expressed in bits as opposed to bytes. Is that a little bit confusing? Well, maybe. But just understand that, of course, we have 8 bits inside of a byte. Contrast with baud rate. So baud rate, of course, can be for analog stuff. It's how many times does the electric state change per second. And, this is used for things like modems. Because what do we know about a modem? Modulator, demodulator. Is that an analog signal coming in or a digital signal coming in? Analog. So you're going to see baud rate a lot of times for that sort of stuff. But you could also see bit rate because what happens once it's converted? Well, you're in digital. So just kind of make sure that makes sense to everyone. They sound kind of similar, but they're quite different. Does that make sense? So in electric state change, what does that mean? If I have a switch, this light switch right here, is it on or off right now? It's on. We have lights. Now what is it? So imagine if I were just to be like a little kid and just kind of go like that. If we were to measure the baud rate, it's how many times can that switch change from on to off? Okay? I always kind of want to do that in the middle of a lecture. You know what I mean? Just kind of turn the lights on and off. Make sure everyone's awake. Anyway, fantasies aside, looking at this and seeing baud rate is all about electric. Now, does it have to be completely on to completely off with baud rate? First of all, is completely on, is that the same measure across different circuits? If I have a circuit that's 120 volt, and I have a circuit that is 240 volt, okay, we're going to see the same amount of change in a baud? Not necessarily. So don't think of this as being something where it's like number of bits per second. That's a very concrete measurement. We know exactly how much data is in a bit. A baud is very specific on the circuit. Going from on to off. Doesn't even have to be on to off, by the way. Imagine we had something like analog audio. We got any audio files in here? Anyone like audio? A few people, okay. So, thinking about how that changes. What happens with a sound signal if we're going in an analog file? We're to change state. Do we have to go from volume to no volume? Or can we go maybe reduce the volume? So baud rate gets a lot complicated, and just kind of understand, for the most part, when we're talking about changes from on to off. Doesn't have to be on to off, though. Does that make sense? All right. Let's talk about half versus duplex Ethernet. So half duplex, I'm going to tell you, you'll probably never see it in the practice. If you think back to, I think it was chapter 3 where we covered the different types of Ethernet cables. Do you guys remember how some of them were only using one single pair? That's using half duplex. Is that going to be very fast? No, it's not. Because basically, what we're doing is we're using a single pair. So we have 8 individual cables, 4 pairs. Isn't it kind of crazy that you have all that and you're using literally 2 out of 8? Isn't that kind of crazy? So with that, you're going to be very limited on speed. It's going to be very prone to congestion, a lot of problems. It's the reason we moved to full duplex. Number one, with pretty much all the cat cables except for maybe like some of these RJ11, you're already going to have basically your twisted pairs. You got 4 twisted pairs, a total of 8 individual strands. So even with full duplex, we're still only using 2 of these pairs. So only 2 of these are actually having any data across it. What are we doing with the others? Are they just there for fun? So think about 802.3f. What is that? Power over Ethernet. Okay, so we're either using the outers, or in some cases we're using both of them. But most of the time we're using just the outer 2 cables to transmit power. What's the advantage of doing that? Well, there's several. Think about regulations involved in doing things legally, of course. Not like what I would do. Well, I shouldn't say that on the recording. What I would totally not do. Just kind of be clear there. So basically, if you're running power through an attic, how do you do it? Any electricians in here? Anyone ever done this before? Okay. There's a lot more, just understand, a lot more regulations involved with running 120 volts than the voltage for this. I think the voltage for that is, or I don't know about voltage, but I think the wattage is usually around 20. Someone check me on that, but I think the standard is either like 24 or 19 or something like that. But that's not the only standard. There's a bunch of different varieties of it. Some manufacturers have proprietary versions of PoE. Ubiquiti is very infamous for having their own standard for PoE, or I think it's like 11 watts or something weird. I don't remember exactly. But basically, just understand that when we're talking about PoE, it's not using the data. So we have additional cables we could make use of. Does that make sense? Okay. So like I said, transmit and receive at the same time. What's the advantage of that? Why is it good to be able to transmit and receive at the same time across the same cable? Yeah, so it's going to reduce congestion. It's going to improve speed. Ceteris paribus, of course, because half duplex. Can we transmit and receive at the same time? Not on the same cable. Whoops. So imagine if we were doing a network and we were building it out, we're only using half duplex technology. Not only is that going to cut our speed in half, it's going to cut our speed in more than half. Why? Because if we can only transmit and receive at the same time, there's going to be some inherent buffer period to switch from transmission to receiving. And that's going to happen over and over and over. Okay? Understand this stuff doesn't happen instantaneously. There's going to be some inherent latency involved. So talking about this, it's also going to avoid collisions. I wouldn't go so far as to say there will be no collisions. I kind of disagree with the book a little bit there. It's going to greatly reduce them, though. And then it's kind of funny to think about. The book makes a big point about hardware must be compatible. Well, what hardware built in the past 30 years isn't compatible with this? I mean, I'm sure there's some stuff somewhere. But for the most part, anything that's, semi-modern, or especially modern, it's going to be compatible with full duplex. So don't even worry too much about that part. We're going to talk a little bit about Ethernet and the data link layer. Like I said, it's done via MAC address, and of course this is going to be hardware addressing. It's specific to the piece of hardware that we're on. So let's talk about binary conversion, and we'll come back to MAC addresses in a little bit more detail. So we have nibbles and bytes. So when we're talking about the differences between these, of course, nibble is going to be 4 binary characters, whereas a byte is going to be 8 binary characters. We're talking about binary, we're talking about 0 or 1. So what we do is we kind of look and see what are the values associated with these. Well, it's quite simple. The first is either 0 or 1. Second is either 2 or 0. Third is either 4 or 0. And lastly, the fourth character here is going to be either 8 or 0. Does that make sense? But it's going to be 1 that you'll see represented. So imagine if we had, in fact, I'll write it over here so I can actually reach it. So the 8, and that's going to be represented by a 1. Does that make sense? And we have second position, it's going to be the 4, and the 2, and the 1. So that's what that would look like. So if we were to represent the number 15 using binary, it would be this. Okay. So looking at this in a little bit more detail, how many values can we represent with a nibble? What's the number of values that can be represented with this? So what do these add to? What's 2 plus 1 plus 4 plus 8? Okay. Now don't say 15 for the answer, because remember, that's assuming we have at least 1. Okay, if we have just straight zeros, what's that going to be? That's going to be 0. Can we also represent 0 with a nibble? Yeah. Most things in programming and that sort of stuff, they start at 0. That's why. Because why they start at 0 and not 1. No. You may not like it, but it doesn't matter. It's how reality is. So let's say I were to represent the number 10. Okay, how am I going to do that? How do I represent the number 10? Well, let's just look at our good friend, the binary here. Okay, so if we want to get 10, how could I do that? Well, I could say, go ahead and start off with 8. Okay, so we have a 1, and then we go over, how many more do I need? I need 2 more, so just go to the 2. So 1, 0, 1, 0. Does that make sense? That's 10. Someone throw me another number between 0 and, between 0 and 15. Any number. 12? Okay, great number. Okay, so 12. What are we going to do? We want to get 8 plus 4, right? Okay, so all we have to do is just get our first two positions. That's going to equal 12. Does that make sense? So all we're doing is just adding in the 8 and the 4, and then everything else is going to be a 0. All right. Let's talk about bytes a little bit. So bytes, of course, just extend this beyond. So we also have 16, 32, 64, and 128. Okay, so 1, 1, 1, 1. All right, does that make sense? Someone throw me a number between 1 and 255. 88, okay. All right, this is where we're going to get out a calculator because, you know, I don't want to do this wrong in front of everyone in a recording, make a fool of myself. Anyone have a calculator with them? So basically, like I say, we know that we can't have 128 because is 128 greater than 88 or less than 88? Appreciate it. So we're going to start at that top number because we know that 188 is less than that. Got a 64. Since it's greater than, where'd I put the marker? So again, to represent this, just say 0, 1 for 64. So we're just going to do 64 plus now. So if we just do like 88 minus 64, gives us 24 left. Is 24 greater or less than 32? Less than. So we know this next number is going to be a 0. Now, of course, it's going to be 24 is greater than 16. So we just go ahead and put our good friend the 1 there. So take 24 minus 16. We got 8 left. Okay. Luckily for us, what's the next character? It's 8. So we got a 1 there. And of course, 8 minus 8 is what? 0. So everything else is going to be zeros. All right, does that make sense? All right. Who's brave? Who wants to do one on the board? Any volunteers? Ben, you're looking awfully intent like you want to do this. All right, didn't mean to shock you there. Sorry about that. Someone throw Ben a number 0 and 255. 130. All right, Ben, so what are you going to do? It's really not bad at all. 128. Looks right to me. So that's kind of how we do it. I'm just going to set the calculator here because we're going to use it in another slide. But everyone clear on this? So let's say I give you a problem on the exam, and I'm a mean guy, so I say no calculators, okay? Don't know if I will or not. I might. You'll probably see this sort of thing in this level on the CompTIA exam. So I probably will throw one basic conversion like that on here. So let's say you don't want to memorize all these numbers. Well, all you have to do is just understand the first number is either 0 or 1, okay? And coincidentally, the value of it's also it represents a 1. So then all you have to do is just, start going up by squares. So you start at 1, of course you go 2, 2 squared, of course 4, multiply that by your good friend 2, gives you 8, 16, 32, 64, 128. Okay, does that make sense? So don't worry about memorizing all these values, just understand what they represent. All right. Now let's talk about going from hexadecimal to decimal a little bit. So I have up here on the board, I have the hexadecimal value, which we know is anything from 0 to F, and have the binary value associated with that. Now one of the cool things about this is these binary values, what type of values are they? Are they a nibble? They're a nibble. Okay, so this is all about what the nibble represents. Okay, we can go anywhere from 0 to 15, just like we just did. So is this going to be very difficult to convert? No. Is it going to be very time-consuming and a little bit tedious to convert? Yeah, I'm just being blunt. It is. So having said that, kind of look at this. We have the hexadecimal value anywhere from 0 to F. The binary value associated with that, of course, 0 is going to be represented by 0. Then, of course, as we go up to, say, F, it's going to be 1111 because the decimal value is 15. So the decimal value is going to be the same until we run out of single-digit numbers. So why can we not have 10 right here? 10 is the decimal value. How come it's not the hexadecimal value? But how do you represent a difference between 10 and 10 in a single string? So you can't. That's why we go switch over to numbers. Of course, think about the numbering system we're on is base 10. 0 through 9. How many digits rather, do I represent 0 through 9 with? 1 digit each. Okay. Anything greater than 9, how many digits do I have to have? At least 2 digits. Does that make sense to everyone? Did I lose anyone? All right, so with this in mind, let's say I were to throw a little bit of a curveball. Let's say I were to do, say, 1001 and then 0000. Convert this binary to hex. So how do we do that? So right now, let's ask a question. Is this, so we know this is binary. Is it a nibble or a byte? A byte. How do we convert a byte to a nibble? How about we just cut it in half? How about that? Okay. 1001. What is that going to be in hex? Okay. So we come look up here. 1001 is, of course, 9. 0, 0, 0, 0. Please don't miss this one. What is that going to be? It's going to be my hero 0. Okay, so converting this binary into hex is going to give us 90. Okay, so that's how we would do it. And this is how MAC addresses are formed. Of course, we have 6 pairs of hex. So we're going to talk about that in, I think, the next slide. But someone throw me some other binary, byte, I mean. Any byte at all. One 100 1010. All right. So, calling someone different for this. Who wants to take a stab at how we would convert this to hex? Anyone want to take a stab at this? All right, so what's the first thing we do, guys? Cut it in half. Get ourselves some nice little nibbles. Maybe we have too small of a bite, so we have to nibble. That's the last pun for today. So, 11. Well, it's not 11, but, you know, I'm going to call it that. So looking at this, what's the first value? It's going to be 8. Second value, it's going to be 4. This is 12, okay? So if we go 0 through 9, that gets us, of course, up to 9 because we start at 0. And we go to 12. Okay, what's the 12th character inside of hex? C. All right, same thing over here. We got 8, and we got our good friend 2. Okay, so what's that? That's 10. What is that? Okay, so we have CA. All right, everyone clear on this? Like I said, make sure you understand it. Thanks for letting me borrow your calculator. And yeah, shouldn't have any major problems with it. Like I say, I'm not going to throw like a huge, you know, I don't know, 8 bytes to convert. I'm not going to do anything crazy like that, but I might give you a single byte, and I might say convert this to decimal. And kind of go back to the rules here. Think about the byte. Convert that to decimal. All you guys have to do is add up the ones. I might give you a byte and say convert this to hex. And all you guys have to do is split it into nibbles, convert each nibble, concatenate them. Pretty straightforward. This is about the extent of what you'll see on the Network Plus. You know, my opinion is that it's kind of silly to to spend a whole lot of time talking about it, so spend about 5-10 minutes. But here's why this is important for networking. Well, several reasons. So the data itself is always going to be transmitted in binary, and we'll get to that in a couple slides. But MAC addresses, of course, are going to be hex. So 48 bits, and in total, they're going to be 12 nibbles. So with hex, we know that a nibble is equivalent to a character. Okay, so it's 12 characters, 6 bytes, and a lot of times they're going to be represented, or we have the byte, and use a colon to represent them, or that's supposed to be a colon, not a semicolon, by the way. You could also use dashes for each pair. So we have like 0, 0, A, that sort of thing. Don't mix and match. Pick one and be consistent. So, kind of looking at this, there's 4 major parts of it. So the first part is going to be defined by the IEEE, which is going to give it to you as a vendor. So for example, if I'm a vendor and I'm making network interface cards, I go to IEEE and I say, I would like to have an organizationally unique identifier. Okay? And then from that, I also have to have the individual or group. You can tell us if it's unicast or multicast, which we're going to cover in more detail in chapter 6, or as well as local or global. This is where I was talking about, it can either be something that's going to be permanent, or it can be something that's going to be variable. And when I say variable, I mean it can potentially be modified. It's going to be a lot more relevant in IPv6, where we may want to have the IP address that the device is on, which will be unique to the device, at least as of right now. Possibly could change in the future. Who knows? Right now, though, unlike IPv4, we're not using network address tunneling. If you have an IPv6 address and that's what you're using, that is going to be given to the world. So you could hypothetically include your vendor assigned part inside of that, and that's where you would use that sort of a more global address there. Does that make sense? All right. So, like I say, the first, and let's actually take a look at some of these. I think this is important. So I've got the Wireshark OUI lookup tool that I just kind of linked here. So I'm just going to pull it up briefly, and we'll just go through an IP address. Or a MAC address, I mean. Goodness. All right. So, anyone want to give me a MAC address? Any MAC address at all? All right. So I think Ben probably made this up. Either that or he's very good at memorizing things. Probably more likely to made it up. So what this is going to do is this is going to look up this part right here, which is, of course, going to be the OUI, Organizationally Unique Interface. And we'll see if this is actually going to match something. So it doesn't match anything. Let's get a little bit crazy here, and let's use my own. MAC address isn't going to be touching the network. I'm not too worried about this. Well, it will be touching the network, internal network. I probably shouldn't do this with my laptop. Yeah, that's not a good idea now that I think about it. I don't want anyone in here to get any ideas to mess with me, so yeah. But that's basically what we do. We just put in a MAC address here, and it's going to be able to return the manufacturer of the network interface card. So does that mean that the network interface card, actually I'll tell you what I could do. Instead of giving you the exact MAC address, I'll just make up the last 6 characters that you guys won't know. Alright, so, like I said, this is not going to be my actual MAC address, but it's going to be close. Alright, so this should return something because this part is pulled from my actual hardware. Well, it should. Well, most of the time it would. Not really sure what's going on there. Not going to worry about it too much. Just understand that they have an API. So let's say you're programming an app and you want to make sure that someone's actually on the device they say they're on. There's several cases where you may want to do that when it comes to networking. For example, let's say that you are running a residential network, like for example on campus. And let's say they have one network that is specific to media devices, like Xboxes, PlayStations, Roku's, Fire, all that sort of stuff. Basically, if you use an API, whatever people put in, verify that it is in fact using an OUI that is recognized. Why would you want to do that? Well, do you want to have a lot of non-media devices on a device that maybe has fewer protections? Is that a good idea or a bad idea? Could be a pretty bad idea. So just kind of keep that in mind with the MAC addresses. All right, let's talk about Ethernet frames a little bit, and let's go ahead and erase the board so we can see things just a little bit. Because this is where it gets kind of important to make sure you understand everything here. So with the Ethernet frame, we know this is happening inside the data link layer. Okay. Think back to the different layers in OSI. Where is data link? Is it at the very bottom, or is it close to the bottom? It's not the very bottom, but it's close to the bottom. Of course, the very bottom is physical. So above physical, you got data link. And what this does, this takes bits into bytes and bytes into frames. And the frames, of course, now does it just do it in this one direction? No, it goes both directions inside of here. Why? Because we convert things transmit and receive across the network. Like when we're talking about the different data frames, they're not just one direction, they're multi-directional. So looking at these different parts here, there's Ethernet and 802.3. We're going to talk about them both. There's really only like one difference between them. They either have type or length, so not a huge difference. Let's go through the different parts of them. So the preamble is going to be alternating ones and zeros. And the purpose of this is to tell where the start of the packet is. And in total, this is going to be a total of 7 octets. So, it's going to be quite a long thing. We think about octet. It's going to be 1, 0, 1, 0, 1, 0, 1, 0. 7 of those. Okay? Somewhere in there, we're going to have the start of the frame delimiter, also referred to as a sync. And what this does, it's going to have a 1, 1 in here somewhere. And the purpose of that is to help identify. If we have alternating ones and zeros, at some point we have a 1, 1. That's going to be the start of the actual packet. Does that make sense? Okay. So then after that is where it gets a lot more intuitive. We have the destination address. So think about what a destination is. If you're sending a postcard to your friend, okay, destination address, what's that going to be? It's going to be where it's going to. Only in this case, it's going to be the MAC address. So you'll notice up here I have a bunch of F's. Are we paying respects in chat? We're just sending this out to everyone. Okay? It's going to be a broadcast address. So in hex, what is an F? 15, exactly. That's 12 15s. Okay? So kind of think about that and understand that's what we're doing there. Now, with a source address, we cannot use a broadcast address. Must use the actual MAC address it's coming from. Why do we have that protection in place? Well, how do you respond to everybody? Is it possible to respond to everybody? Yeah. Would that be annoying? That'd be pretty annoying. So that's one reason, but it's really a lot of different reasons. Imagine you're writing malware, and they didn't have this protection. Okay, is it a good thing to know where something is coming from? Yeah, it's quite a good thing. So that's why you have to use the actual MAC address there. Else, the hardware won't allow you to actually send it. So switches and routers will reject the transmission, and if you don't use the actual MAC address. Does that make sense to everyone? All right. So like I said, the difference here, 802.3 uses length to identify the packet type, whereas the Ethernet uses just the type to identify the packet type. Don't worry too much about that. That's covered in more detail in chapters 5 and 6. Data. So as the name would imply with data, it's going to be the actual data. So whatever the actual packet needs to contain, that's what we're going to have there. And lastly, we have the frame check sequence. All this really is there for is to close out the packet, store our good friend the cyclic redundancy check. All right. So just kind of wrapping up here, we've got a couple more slides. Ethernet at the physical layer, the whole thing is just reviewing cables. Okay, we just covered cables like not even a week ago, so just make sure you understand the different types of cables. Especially make sure you understand Cat5 and up. Make sure you understand the common types of fiber connectors, straight tip, square tip, all those. Just make sure you review those. Not going to cover it again. Really no point. Other standards of Ethernet, IEEE 1901. So we're talking about transmitting Ethernet signals over a power line. This has a lot of exciting possibilities and also a lot of potentially scary possibilities. So again, I'm not here to talk conspiracy theories or anything, but this is an IEEE standard that allows your ISP to be the same as your power company. Now, if you're like me, you live out in the sticks, this is a really promising technology because is there already existing power technology run? Yeah, I don't use like a daggum windmill or anything to get power. I have power, but is my internet service very fast? Pretty terrible. So imagine if La Plata Electric Association, and they're actually in talks to do this right now, by the way. If you're a member, I recommend you read your bill. They've got some information on there about it. You do you. I'm just saying. Anyway, they're considering offering internet service. Now, would that be a good thing or a bad thing? Is anything going to be a purely good or a purely bad thing? Probably not. I would probably very strongly consider getting their service because it's probably quite a bit faster than my existing provider. But what this also enables is, imagine if your refrigerator or your oven or whatever, water heater, even kind of scary. Imagine if your furnace had a direct connection that would give all sorts of information about consumption to your power company. You guys remember the story where in Texas they had people who got the like a Nest and other sort of smart thermostats. What happened to them when their power grid was having trouble? What happened there? Yeah, they shut it off, or they turned the heat way down, or they turned the air conditioning way up. Is that something you want to have happen to you? I mean, I'm not here to say that it will, but I'm here to say this technology, according to the standard, it enables it to be possible. So again, make of that what you will. The advantages and disadvantages. So it can allow each device to not only communicate, but to be controlled. Now, assuming the device also enables it, because let's say you have an old refrigerator from the 90s. Do you think it's going to have the capability of transmitting anything? No. But, modern smart fridges, who knows? We may see an example of that happen where maybe the power companies control things. Maybe they don't. I don't know. Does that kind of make sense to everyone? Like I said, I'm not saying that this will happen. I'm saying standard says it can happen. So, look up the standard. Don't take my word for it, but just kind of understand that. Then the other standard we're going to cover, Ethernet over HDMI. There's a couple things we may use this for. As the name would imply, what we're doing is we're taking an internet signal over LAN, of course, and connecting it into a device. That device is having HDMI cables come out from it. The HDMI cables, in addition to carrying, so they carry, of course, video signal, and they also carry, of course, audio. If you have an HDMI Ethernet-enabled device, they can, of course, also share an Ethernet signal. So a lot of advantages and disadvantages for that. If you have a home theater, that's what the example of the book. They have like some sort of DVR, maybe some sort of, I don't even know what all this stuff is. I don't know. So I guess it's like a streaming box, got an internet symbol beside it. It's probably like a, I don't know, DVR maybe. This is like a Blu-ray, DVD player, whatever the hell this is. Doesn't really matter. Just imagine each of those devices are getting an Ethernet signal from HDMI. That's not all this is used for, and I think more interestingly, and why I actually chose to cover this topic, because think about a remote signage. Would it be possible to run only 1 or 2 cables and have a TV anywhere that has real live updates? Well, yeah. So you could, if you wanted to have Ethernet be transmitted, you could certainly do it this way. You could also theoretically reduce the number of cables using like a thin or a zero client or even a terminal. But what's the problem with doing that? Okay, so if we're doing it this way, what is the problem here? So if we had a thin client, okay, what is the point of getting an HDMI cable run across a ceiling, for example? What's the point of that? Well, there's not really one. It's theoretically possible. You could do it. But what are you more likely going to use? So to reduce the number of cables, you can instead use PoE. So you have an Ethernet signal coming into the device, and it also provides it with power. So you basically only have a single cable that provides power and Ethernet signal. And most of the time, even with a terminal, you're going to be able to get the video signal from the actual device as opposed to from a server. Does that make sense? So there's some rare cases in which it may make sense to do this. Most of the time, just use PoE. All right, just kind of wrap things up. Talked about network basics. Talked about different communication standards a little bit. Talked about binary to hex and all that sort of stuff. And wrapped up talking about just a couple alternative standards. Any questions about today? All right, make sure I end up with a thank you cards. I'll get those over to, thanks. I'm going to get those over to the network team. Have a great day, guys.